Hi guys, Lauren Smith here. I got a H1 in Physics and Maths and I'll be walking you through 2020's higher level question 9. Today's long question is on the topic of sound, in particular resonance, fundamental frequencies and magnetic fields. So let's get into it. Okay, so here's the first look at our question 9. Now we are told that in acoustic guitars, resonance occurs between the vibrating strings and other parts of the guitar. This information leads us into parts 1 and 2 of our question. And in part 1, we are asked to define resonance. Just a simple definition question, but it's still handy to go through because we want to see where we get our marks from for this definition. And our definition is that resonance is a phenomenon and it occurs if the frequency of a periodic force applied to the body in question is the same as or very near to its natural frequency. Then we have a transfer of energy and the body will vibrate with a very large amplitude. Okay, so where do we get our marks? Our first set of marks goes for the phrase transfer of energy. Now, it's very important to mention this in your definition for resonance because, as we know, sound is a form of energy. Resonance is a phenomenon of sound waves, and therefore it is useful to describe phenomenon with sound in terms of energy. You'll get 3 marks out of 6 for stating this. Now, where are your other 3 marks coming from? Well, if you say something like that it happens between 2 bodies of the same natural frequency, or in my case, if you say if the frequency of a periodic force applied to the body is the same as or very near to its natural frequency, both are synonymous with one another. Perfect answers and you'll get your other 3 marks, giving you 6 out of 6. Now in part 2, we're asked to describe a laboratory experiment to demonstrate resonance. Now this is a demonstration question where we have to explain or demonstrate an experiment which we would go through in the lab. They're the quick experiments that you all have to learn off for the exam. How I would structure out this answer, and this can be said for very generally for all your experiment questions, I would structure them apparatus, method, observation, because in the marking scheme for these type of questions, you'll get 3 marks for your apparatus, 3 marks for your method, how you're going to do the experiment, and 3 marks for what you observe, your observations, which are very important in physics. The apparatus and the method, though, they can work very well with one another. If you know the apparatus, then you know the method, because if whatever you're drawing, you're going to have to explain why you're drawing everything, what's the process, what's happening. And the same can be said for the method. If you know the method, it's very easy to construct the apparatus from that. But always, always, always have both a pictorial explanation of the experiment, the apparatus, and also a verbal explanation, which is the method. So getting into it, let's first look at the apparatus. And here it is. You might have seen something similar to that if you were doing this demonstration out in the classroom or in your notes or whatever. But my apparatus is this. We have 2 tuning forks, which are going to be the 2 bodies of the same frequency, because this is the whole idea behind resonance as we looked at our definition earlier. And with tuning forks, it's easy to ensure that the frequencies are the same for these 2 bodies. And I have here that we strike the tuning fork on a table and we have the vibrations of tuning fork 1 over here in magenta. And therefore we have the resonance vibrations from tuning fork 2. These are in purple. Now I've outlined them with dotted lines because we know that they're kind of secondary vibrations. They're not the strong vibrations which we got by whacking tuning fork 1 off the table. And we have this transfer of energy here. The vibrations from one fork are being transferred to the other fork. When all is said and done, you'll get 3 marks for this apparatus. Now moving on to the method, which is what we're going to describe this apparatus out in words. The method is as follows. We are to strike a tuning fork and set it vibrating, and hold it near but not touching to another tuning fork of the same frequency. Keywords here are going to be same frequency, going to be that the forks are near but not touching. And also, it's a very important point if you're detailing out your method, how you are using the apparatus. The apparatus here being the tuning fork, and what you're going to do is you're going to strike it to set it vibrating. Always use a verb along with the apparatus in order to really flesh out that answer. Now, next we have the second tuning fork will also vibrate, and it can be heard doing so if you stop the first fork from vibrating. And finally, if we were to repeat the above procedure with two forks of different frequencies, and the effect is much less noticeable. Again, repeating procedures with slightly different parameters in physics is very important when you're drawing your final observations and your conclusions. Now, this is the full method, and you'll get 3 marks for these 3 points. Now, what do we want to conclude from this experiment? What do we observe from these procedures? And how can we conclude? And how can we make conclusions from them? Well, the conclusion that I've put in is as follows. The first tuning fork exerts a periodic force on the second tuning fork. And the second tuning fork only vibrates with large amplitude if its frequency is the same as or very near to that of the first, which demonstrates resonance. So you have demonstrated resonance and you explained how it's done, basically the theory, the observation behind it. Very, very similar to the actual definition of resonance, which we looked at in part 1. And for this conclusion, or your observations, you'll get 3 marks. Okay, so we're going to go back to the original question because we're given a little bit of information which will help us answer parts 3, 4, and 5 of our question. We are told that a guitar string has length of 2 meters and a mass of 0.88 grams. Noting that we're probably going to have to change the mass measurement into SI units, which is the kilogram, for a unit of mass. We are told that it's stretched across 2 fixed points, which is important to highlight, and we'll see why that is in part 3. And we are told that these points are 65.1 centimeters apart on the guitar. It is then plucked and it vibrates at a fundamental frequency of 330 hertz. And with this information, let's first go on to part 3, where we are asked to draw a label diagram to show a guitar string vibrating at its fundamental frequency. It's not an open pipe or closed pipe, which we are normally used to seeing when we're doing these fundamental frequency diagram questions, but it is in fact a guitar string. Now, a guitar string itself, it's held down at both of the ends. Therefore, we can compare it roughly to the pipe closed at both ends, say, if we were to have some sort of instrument like that. And therefore, your diagram will look something like this, where we have the guitar string at its fundamental frequency. And think of when you pluck a guitar, you pluck it from the middle of the string, and we have the ends held down by the pegs. Since they are held down at the very ends, we're going to have nodes, or I denote them as N. I have this little key down here, which I would recommend you to do in the exam, so as to make your diagram as clear as possible and to convey exactly what you want to convey to whoever is marking your paper. Now, we have nodes at each end because they are held down, so we're not going to get any vibration, no energy there. And you're going to have your amplitude in the middle. And this would be the fundamental frequency. The, I suppose, simplest way you can have this laid out, this frequency here. So we're going to have our antinode in the middle. It's going to have the highest amplitude, and our nodes at the end. These are the key components for all of these types of diagrams here. For showcasing that you have the nodes at each end, you'll get 3 marks. For putting your antinode in the middle, you'll get another 3 marks, giving you 6 out of 6. Before moving on to parts 4 and 5, I want you to draw your attention to page 59 of the Formula and Tables book. In particular, we're going to be looking at the fundamental frequency of a stretched string equation, but we're also, for part 5, going to be looking at the velocity of a wave equation. And in part 4, we're asked to calculate the tension in the string. And from the question, we were given loads of information. We were told that the length of the string, which I'm going to denote by this capital L here, was equal to 2 meters. We're told that the frequency is 330 hertz. We are told that the mass is 0.88 grams, but like I said earlier, we're going to have to convert this into SI units, which is the kilogram. And we get that the mass is 0.88 times 10 to the power of minus 3 kilograms. We're told that the length between the 2 points which are held down in the string is 65.1 centimeters or 0.651 meters. I've denoted this with a lowercase l like you see in the formula, since this is the length over which the vibration occurs. Now we're going to be using the formula you can see to your left here. This makes the most sense since it includes this variable here t, which is the tension we are looking for in the string. We have all the other variables, we even have mu, however, we need to calculate it. But before we do that, I just want to mention that this formula, just directly copying it from the formula and tables book without doing any calculations whatsoever, will get you 3 marks. How do we calculate mu? Well, mu is the mass per unit length. We have the mass of this string, it's this figure here, but we also have the length of the string, denoted by this capital L. This is why it was useful for the question to mention it to us. So let's calculate mu first before we do absolutely anything with the formula in order to calculate the tension. Since we're talking about mu as the mass per unit length, the formula itself is self-explanatory, hence probably why it's not mentioned in the formula and tables book. However, if you would like to learn off your formulas, if that would make you more comfortable going in with the exam, I would suggest learning this formula off. You're not going to be able to find it in the formula and tables book. How do we calculate it? Well, we have the mass as 0.88 times 10 to the power of minus 3 kilograms. Just putting in those units there. And that's all the way over the length, which is 2 meters. A simple calculation will tell you that the mass per unit length is equal to 4.4 times 10 to the power of minus 4 kilograms per meter. And it's a good idea to also, if you're calculating these little things, to keep your units on hand, so you know what units you're going to end up with at the very end of your calculation. So we have the frequency, we have the length over which the vibration occurs, i.e. where the string is fixed down. We know the mass per unit length, but we want to know the tension. Now we're going to start to manipulate the formula in order to find this T. However, before you do that, you will get another 3 marks for calculating the mass per unit length, either by roughly stating this formula here, which will get you 3 marks, or you can attain these 3 marks by actually doing out the calculation as you see here. Either or will get you these 3 marks. Now we're up to 6 marks now. As I said before, we need to manipulate this formula here because we would like to get all our known variables, which are f, l, and mu, in terms of the target variable, which is t. If we multiply both sides, first of all, by 2l to get rid of this fraction here, we're going to get line 2, as you can see here on the screen. Now to get rid of this square root, which encompasses the t, we're going to square both sides just to get rid of it, and this will lead you to line 4. And again, we just want t on its own, so we want to stop dividing it by mu, or the mass per unit length, so let's multiply both sides by mu, and we're going to get this final line here, that t is equal to 4 l squared f squared times mu. Now, very important with all of our figures, which we have gotten through by the question or what we calculated, we need to substitute them into this expression here to get your marks. And just substituting them in, which is proof that you've correctly manipulated this formula up here, will get you 3 marks. To get your final 3 marks, of course, you're going to have to input this into the calculator correctly. So let's do that. We have 4 times 0.651 squared, that's the length, times the fundamental frequency of 330 all squared, times the mass per unit length, which is 4.4 times 10 to the power of minus 4 kilograms per meter. Since we are using operations such as multiplication, we're also using scientific notation, we're also squaring numbers here, it is best to use brackets so that it's absolutely clear to the calculator what way in which you want to calculate this whole expression. Okay, so clicking equals, we finally get the tension. Since tension itself is really rounded to the nearest whole number, you hardly see instrumentation with decimal or fractional measurements for the tension, so it is best to observe that convention and just round it to the nearest whole number, giving us 81 newtons as the tension. The newton is the unit for tension, since tension is the force. This gives you your final 3 marks for your question, giving you 12 out of 12. In part 5, we're asked to calculate the speed of sound in the string. And we're going to do this, like I said earlier, in page 59 of the formula and tables book, by using the formula v is equal to f lambda. This v in the formula and tables book is also denoted by a c. However, I'd like to use a v in this case because we're looking at the speed of sound of the string, and c is usually denoted as the speed of light, just to avoid confusion. Now, we know what f is. F is the fundamental frequency of 330 hertz. However, what's lambda? Well, we know at the fundamental frequency, the string is vibrating at half a wavelength. since as we saw in part 3, we had 2 nodes at the end, and at the fundamental frequency, we had 1 antinode up here. And this clearly is half a wavelength, and half of a wavelength is represented by the length over which this vibration occurs, which is 0.651 meters, of course. So therefore, half a wavelength is just this length measurement, this L here. So we can find what lambda is, or the full wavelength of this sound wave. So we have lambda is equal to 1.302 meters. Substituting this into this formula, we have V is equal to 330 hertz times 1.302 meters, which we will now put into our calculator. There's the frequency, there's the wavelength. Hitting that equal sign, we have an answer here, which is roughly 430 meters per second. Okay, so now we're finally at the end of this calculations question. Where are we going to get our marks? Of course, you're going to get marks for your formula, which is why it's always so important to always put down your formula, as I keep saying. And you're going to get another 3 marks for your final answer. Please don't forget your units. They're very important, and you will lose marks if you forget them. Okay, again, going back to our question for the last 3 parts of question 9. We are told that in an electric guitar, a magnetic pickup detects the vibration in the string. So we're going to be talking about magnetism now. Now we're told that this pickup consists of a stationary magnet and a coil around the magnet. And when the string vibrates, an EMF is induced. And this leads us nicely into parts 6, 7, and 8. In part 6, we're asked to draw the magnetic field around a bar magnet. And this will be a relatively straightforward diagram, with the key points being that we need to have the correct shape to describe how the magnetic field is, and we need to have the correct direction, okay? So which way is this magnetic field going? And we're going to have something like this. Here I have indicated the north part of the magnet and the south part of the magnet. The shape is circular around the sides of the magnet, and it is spreading out. So we have small circular one here, and they extend outward like so. So the correct shape, circular, we'll get you 3 marks, and the correct direction is just from north to south, as you can see here from all of these lines that the arrows here are going into the south part of the magnet and going away from the north end of the magnet. Okay, 3 marks for the correct direction, giving you 6 out of 6. Now in part 7, we're asked to explain how an EMF is induced in the coil. And the simple explanation can go as follows. We have that since the coil is around the magnet, there is a magnetic field present. When the coil moves, the magnetic field cutting each point of the coil changes with respect to its original position. I'm just going to highlight there that the coil moves. This is a key part here to inducing the EMF. Now we know that the requirement for inducing an EMF in the coil is such that the magnetic field passing through the coil changes, and hence an EMF is induced in the coil. Where will you get your marks? You'll get your first 3 marks from saying that the coil moves, and you'll get your other 3 marks for saying that this changing magnetic field is acting on the coil, or that it is passing through the coil. We know that, giving you 6 out of 6. Now in part 8, we're asked to sketch a graph to show how the output current varies with time. Now we're going to sketch this graph. We don't need to put any exact measurements or anything like that, but we do need to have the important components of a graph, like labeled axes. That's very, very important, and also the shape of the graph. This shows us a rough idea or a sketch of how this relationship with time holds. Now the output current is in amps here, denoted by A, and we have the time in, say, seconds, something like that. When you're labeling your axes, scale them properly, make sure you have the correct variable on either axis, and you have the correct unit for said variable. You don't really need to scale them in this case, since we're just giving a sketch. Okay, but since we're looking on how output current behaves with respect to time, we're going to put time on the x-axis because it's the independent variable. That's not going to change, whereas the output current is going to change with respect to time. And it's going to do so in the shape of a sinusoidal wave here, because we're looking at this output current, which is the alternating current. This is the shape for alternating current here, as you can see. It's going to reach maximum points here, 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 and here. But it's also going to obtain some minimum points here and here. And we're also going to have points, as I've circled on the screen here, where we don't have any current whatsoever. You're going to get, well, it says in the marking scheme, 5 marks for this, 3 marks for having the correct labeled axes or the correct shape of the graph. And if you get both components correct, you'll get that bonus 2 marks. And therefore we are done our question.